I'm the trusted builder for this project, and we thought it'd be a good time to just showcase what we've done here, and hopefully people are able to take something away from it. There's no right or wrong way to do things, but we're just going to show you our way. So yeah, just a short presentation, and after that we'll open the doors and you can look around. You can run through the forest if you want to. There's no wild animals there, so you'll be safe. So there's a program I watch with my wife sometimes called, I think, Lincoln Lawyer, and in there was something that I thought was quite interesting. It said there's three things in life: what you desire, what you believe, and what you need to do. This project is what we needed to do. The first two sort of came through as secondary. So the school here is based on Gaia principles, which the client is very passionate about, which relates to basically the earth. So there's a lot of things relating to that in here that you'll see. And perhaps, at the end Darius might say a few words if you might want to just let you know a little bit about that. So this is it. This is the site. I just realized that lasers don't work on bright things, so this is the laser somebody found me. So this is where we are. And this obviously is the long driveway. You walk down, you park probably somewhere there. And this used to be a building like that. So currently we're probably sitting somewhere in here. And that really, the site's quite big. As you can see, it's around about 10,000 square meters in the heart of myriad, all surrounded by all residential streets and so forth. So it wasn't an easy project in terms of consultation. There's a school right next door. As you can see, these playing fields there. There's a primary school there. But eventually, the client obtained resource consent, and we were charged with the job. Now, this is what it was meant to look like. It's sort of pretty close. We've lost a few things along the way, but by and large, it's about there. The thing that this has is, if you can see, that the foundation piles are trying to mimic trees. So as the roots come out from the ground, and then the building sprouts up. That was the idea. There's sort of clear roof or light photosynthesis, so the kids get enough sunlight and perform well. So yeah, these are sort of early concepts. You'll see quite back at the building is quite tall piles. So the building is basically, you at the head height, you'll be within the treetops there. So a very interesting project, and it's meant to resemble a leaf. So all of you have seen a leaf before. So as you walk through, you'll see what it has, what the design philosophy was, and that's kind of almost like a leaf. Now, a few things regarding that is that it's around about 900 square meter floor area, close to. And as with the leaf, you see how you have this little veins coming out. Well, this also tries to mimic that, and this squiggly line through there in red is meant to be the center line, which is not exactly straight center line. Well, we're no stranger to building weird curved buildings, so this is one we did a few years ago, which is shaped like a crescent, quarter moon, wrapping around two trees, which the client also owns. Quite nice, sharp, pointy bits, which you can see there. And obviously we do sort of a range of projects, small and large. Now, some issues. As every project has issues, we all know. The issues in this one weren't too dissimilar to other projects, but some things were worse than others. Sort of the standard stuff: services, asbestos, ground conditions, procurement, transportation of materials, etc., etc. Do you want to hit the light, mate? And a bit of redesign. We also, is that okay for everyone? Yeah. Maybe I can use my pointer now. Would be smart. No. Old school is better. Okay. So I'll walk through the design, couple of the design elements through there. That one of the key things was, as I showed you before, that it's meant to resemble trees and leaves. So we had external sort of beams coming through the roof, which were meant to be the little veins of the tree, and it was obviously needs to be in timber. But there were some fires just prior to us starting the project. So procurement-wise, these were all imported beams, which would have really thrown the project out, and there was a lot of uncertainty about when and costs, etc. And this standard cost escalation, which happens in pretty much 99% of the jobs. And COVID, well, everyone's been blaming COVID for everything in the last 2 years, you know. Everything's COVID. So we were a little bit the same. How do you read that? Well, you read that as dollars, dollars, dollars. That's all it is at the end of the day, isn't it? And why is that a problem? Everyone's got money. What's the problem? Well, the problem is that through COVID, most businesses experienced a huge business downturn. This school, obviously, kids were staying home, enrollments were low, etc., etc. That affects your revenue. Holding costs, debt servicing, general uncertainty, people don't know what's going to happen. So we were asked to basically find some ways of saving money, which is easier said than done. So we came up with some solutions, you know, lots of solutions, but obviously within reason. You still need a roof, you still need windows, so you can't go chopping everything out. So we had some sort of just general basic spec changes, changing balustrades, etc., flooring specs, etc., etc. But those sort of weren't really adding up, so to speak, of what our target was. Our target was 10%. The major thing was a structural revision to try and remove the exposed timber beams. So it was expensive, it was coming from overseas, timelines weren't known, and without a roof, you can't progress much else off the building. So we decided to do something with that. So quick design summary. As you can see, it's a little bit of a complex structure, quite a complex geometry with various lines and projections and things. All of these, you can see they flare out. They're not all parallel, which make our life a bit interesting. Remind you of the leaf. And the central core of the shape. So this here basically was where everything is basically connected to, and it could have been straight, but unfortunately wasn't. So that's fine. We carried on. Were we to complain? So that's, if you look at all those dimensions, no two dimensions are the same. Simon's shaking his head. Yep, he's been there, done that. And if you don't believe me, well, there's some dimensions you can look at. Normally, it's not a big deal. That's fine. You stick in the GPS, you go and mark it out. The problem here is that you don't get GPS signals. They couldn't actually, despite all the technology, the trees that we're trying to protect are not allowing us to do our set out. With the GPS, you walk around and say, well, this point is here, this point is here. In the story, we couldn't do that. Now you go back to third world again and try and use field lights and machines to try and figure out where each of these paths that you see are meant to go. Well, why are they important? Well, they've been designed to obviously serve a function, and the function is as follows. Non-technical people might want to just look away. So there's the steel columns coming down that transfer the load onto this member, and all these old floor joist comes down and into the pile, which I'll show in the next picture. More technical stuff. So the steel comes down into here. There's a plate that's meant to go down into a timber pile. And so far, so good. The size of the pile is 200 SED. SED means small in diameter, so trees they grow like this, so the piles are not completely vertical. They can be a little bit distorted. So this is 200. The inside part is 100. That leaves us 50 millimeters on either side to play with. Now, I've got a gift for this. So if you had something which is the piles there 3 meters. So if you had a pile, this is good now, it comes in handy. If you had a pile that's 3 meters long, we all use the protractors in high school where you measure the little degrees. So 0.95% of a distortion here will give you an offset up the top. Who can guess what it is? There's a prize. The closest answer. No one will get it straight. Come on. 50. The first guy answers because I reverse engineered the 50 millimeters. So there you go. So 50 millimeters. Can you imagine? We've only got 50 mil tolerance. We move this thing by less than 1 degree. We already lost the 50 millimeters. Now, who's seen how a digger operates? Who's seen a digger drilling a hole 3 meters deep? It's a little bit difficult to achieve that 50 millimeters. So anyway, we persevered. We put them all in. But we said, hey, look, there's no way to guarantee. These things are perched 3 meters up in the air. We'll do the best we can. And we put them all in. And then we went ahead and got a surveyor then to go and actually what we call as-built in technical terms. So there's a pile. They would mark the center of every pile. I think there's 240 something odd piles. And they would extract that data so that we could now go and overlay that back into our design and see where the discrepancies are, what's now moved and needs to be adjusted, etc., etc. So we had to do that. Well, we don't complain. So as you can see here, all these, they are not like the sections here are basically 2 sections apart and then they turn. So this one will come in, the next one will come in, etc., etc. And they all got to land on a pile somewhere, somehow. So the load gets transferred. Remember, the tile's already out by 50 mil, possibly. So we carried on with putting all the sort of floor structure in and the leaf started to take shape, which is quite nice, getting out of the ground. You can see the little vein offsets here. They're all kind of staggered. And the internal floor plan was as follows. So again, nothing's really lined up to anything. So, you know, the best I can give you is this wall here is lining up with the other walls, really. And everything else is take it or leave it. So remind you of the leaf again. So I thought, okay, well, look, we need some big cost-cutting measures. We can't be just changing the carpet and save money and all this kind of stuff. So I got out my red pen and a blue pen and said, okay, we need to straighten some things out. Why does it help? When things are straight, the symmetrical load transfers are easier, connection details are easier, spacings are easier, it can be calculated. So this was my go at it. So I tried to straighten up some of these things and make these sections longer so that at least one piece of timber can go across 3 piles rather than having to change direction every so often. And so I presented that to the client and he said, well, what does all that mean? I don't really know. Save me some money. I said, okay, well, I'm passing that. Then we passed it to the structural engineers, which were quite helpful, and tried to mimic what I had done as best as they could, because mine obviously wasn't a structural design, it was just a sketch and scribble. And we almost got there. A lot of things were straightened up. And what that meant is the piles that we had already installed, which were 3 meters high in some places, now with the redesign, some of the piles were being missed. So we've optimized one thing, but we de-optimized something else. So the loading wasn't landing on piles. So what this is showing us is that we ended up then having to go in and put some additional piles so that we could now carry the loading from the top. So that wasn't too bad. And this is what it ended up like. This is basically where things would need to land, 3 meters up in the air. And some insulation and things. So this was another kind of slight issue here, which is the roof is quite a long monopitch roof. I think the distance from there to there was about 25 meters. When there's a reverse slope on something, if there's any water, it will try and get into the building. How do you stop that? There was an issue. And I remember when we had the timber beams in the original design, would have looked like that, and you would have all these basically continuous from the outside into the inside, like the leaf veins of a leaf. The slight problem with that is that the flashing obviously is whatever tries to prevent water. The flashing detail was so complex that there had to be a flow chart for us how to do it. So we wrecked our brains trying to figure out, okay, well, it can be done, anything's possible, but the complexity of that, and remember, there's not only 2 beams, there was 2 beams, we'd do it in a weekend, but there were, I don't know, 50 of them. So every beam, you'd have to follow a process to do this flashing so that the water doesn't track back into the building. So those add cost. Again, it can be done, but they will add cost. So we said, okay, we're going to have to do something about these beams. You can't get them in from Australia. They're very expensive, no timeline. We're going to, what's the answer? Get rid of them. So we did. And we went to a steel structure, nice and straight, easily available in New Zealand. Lose some of the effect, obviously. No trees have steel branches, but it served the purpose. And if you stand outside the building now and have a look at the early concept and look at this, it's close enough to the truth. Right? So the problem also, another problem that we encountered with the roof being 25 meters long, this here from at the widest point is 25 meters long. It was designed as a single run, so it would just be one sheet of iron, 25 meters long. No problem, it's easier, less joints, etc., safer, right? The problem with that is that's the main road. All these black lines are 25 meters long, and that's without the cab that actually carries the trailer. So ignoring that, just the trailer, there's no way you're able to reverse a straight line 25 meters into the site. So lesson here is if there's something goes into the design, you've got to think about how it's going to arrive on site. So the client said, I wish he wasn't here, but he's here. The client said, I don't care. You guys quoted for the job. If you get a helicopter, you need to get a helicopter and do it. Okay, yep. We started looking around for helicopters. The cost for flight time was $10,000 an hour.